So welcome to Advanced Strength of Materials. We'll be covering lecture 8 here, which is a summary of all the equations and the methodology. How will you use this in real life? And we'll do some practical examples later on in this course. So what is the solution approach that we can use? There's 3 governing equations, 6 strain displacement relationships. There are 6 stress strain relationships, as we discussed in the previous lecture. So there's 15 equations, 15 unknowns, and so we're ready now to solve for stress strain and deflections. What are the equations? I have all these equations, but I also have boundary conditions. The boundary conditions is Cauchy's relationship, which relates the tractions to the stress and the normal. So this stress state here is right on that point at very near that surface. And I know that normal to the surface, so I can tell you that relationship. That's a boundary condition. A boundary condition is something you can apply to the body of material on the surface only. This is true at every point inside the volume. Every point. While this here are tractions you can apply only on the surface, and it has clear boundary conditions on the surface. Like say you have a diving board. On this, the view is on the side, that's a diving board. And then you have a person here. Well, that's the traction load you're applying. That's your T. And then these boundary conditions, this is fixed to the wall. That's your boundary condition. This cannot move. The deflection is fixed. It's a boundary condition. And the loads applied here by this human is the tractions applied. So you have your 15 equation, 15 unknowns, you have your boundary conditions, and how you solve this, right? So it's supposed to be 6. The idea here is if I apply a load to a CAD model, I would like to know where the stress is highest. Obviously, it's here in this area there. I would like to do that. And so one approach to doing that is if I apply a load, I want to know where it fails, where the structure fails. And in reality, you can do that. In this example, you can use finite elements to do that. And what finite elements does, it takes all these equations and it finds, and finite elements gives you a good way of solving these equations in an easier way so that you can then plot the stresses, which is what I'm after. Remember how I started this course? I started this course asking the question of how do I predict where it was going to fail so I can design the system for it. That's how we started the class. And guess what? Now I have the equilibrium equations, I have the constitutive law, I have the strain deflection relationship. I can plug the strain into this equation, the stress into that equation. Now everything is in terms of deflections. I have 3 equations here, 3 unknowns, which are the deflections. I can solve for the deflections. Once I know the deflections, I can get the strains. And once I know the strains, I can get the stresses. So in reality, I am ready to go here. The only problem is that these equations look very challenging to solve. And especially if I want to solve it over a very complicated domain like an airplane, it will be almost impossible to do. So what people have done and found a way of doing this is to take this CAD model, divide into small little pieces, which I call elements. These are elements, each of those triangles. And I can choose different element types to discretize that domain. And the idea here is, if I can do that, perhaps I can solve these equations over one of the elements using approximation techniques. And if you can do that, it turns out, I don't want to cover finite elements in this class. I'm just trying to give you the context on how these equations could be used. But you can see here that if I can divide the domain that looks very complicated into small triangles, and I can approximate the solution to these equations over a single triangle, then I do it for every triangle and I assemble a solution for the whole thing, that you can actually turn the very hard problem into a simple one of solving a linear algebraic system of equations. Now, again, this is very top level. I have a whole course in finite elements. I'm just trying to show you how these equations can be used. And then, once you can solve for displacements, you can plug it in here. That gives you stress. Then once you have stress, you can plot stresses. And guess what? I'm plotting stresses there. The stress concentrations near the hole, which is great. That's what I want. So what is the deal here? How do I deal with that? So I have a body of material like an airplane. I input the loads, I put the boundary conditions, I put the material properties, the geometry. I run my model. It could be a FEA model or a hand calculation, which we're going to do. And then I'll interpret the results to know where the critical locations are, so I can redesign if needed. Here, what I'm showing you is a rocket, and every rocket section in this rocket is modeled using finite elements. And they will typically do a dynamic analysis, and that dynamic analysis gives you loads across the different elements of the design. They can take those loads and apply them to more refined meshes or more refined structures. And the idea is to take the section loads that came out of dynamic modeling, you apply that to this finite element, and that gives you the ability to predict the stresses within the model. Here, what you can see is I extracted the cylinder. There's an axial load, a bending load, and shear load. And that can cause failure for the system, for example. And so typically you do the modeling, but typically you want to do a test to verify your model. So here you can see a test done at NASA where they actually apply the same loads to try to validate that model, for example. And typically in industry, depending upon what kind of vehicle you're using, you apply a factor of safety if it doesn't have humans, times the loads that it's going to see in service, and you apply those loads during that test. And then what you see here, all these dots you see here, that's a digital image correlation technique. So you can actually measure the strains across the whole thing rather than using strain gauges. So it's a more advanced technique. And further, I use a 1.25, but you can use 1.4 for human rated. If it's airplanes, it will be like 1.5, for example. And why is testing so good is because analyses, we as engineers will make assumptions, but analysis is very important. And testing is very important. Testing validates your model, which is required because if you're flying an airplane, you can't test the airplane the same way you fly it because the airplane has no boundary conditions, floating in the air. While on the ground is the wheels are touching the ground, but you have to replicate the flight loads. And the only way to do that is to use analysis to show that the test conditions are worse than flight. So you're using analysis to show that whatever you tested is worse than flight. And if you pass the test, then you're good to go. But the only way to do that comparison is analysis. But how you trust analysis? You trust it because you're going to validate it against test data. The strain gauges that you have here, or the digital image correlation, I want to make sure these strains match the finite element model. And that's what I want. I want a correlation between model and test. I want to make sure this matches the stress predicted by the model. And if it's off, then you want to improve the model so then it's useful in design. So moving forward here, you can use finite elements as an example to assess the design of each component. It allows you to look at geometry, dispersions, material properties changes, but you can assess the structural margins. And margin safety is an important quantity using my area of expertise. You know the strength of the material, you can get it from a handbook. In aerospace design, we use the PDS. You can look it up in Google. You can get the strength of a lot of different aluminums. And then you apply the maximum loads that it's going to see in service. That's going to give you this critical stress, say. That stress is what I'm going to put in the numerator. And the factor safety is going to be 1.25 typically for non-human flights. .4 is human rated. And then 1.5 tends to be like aircraft carrying passengers. So there you go. And so if the margin of safety is greater than 0, then you have a pretty good design. Typically, you don't want to design to 0 margin. You want to leave some amount of margin just in case there's a non-conformance. Say somebody drops a tool or the thickness is lower than what you intended. So it's good to keep some amount of a margin above 0 in case there's a problem. You don't have to redesign the system. It will be too expensive. So it's good to keep some amount of margin, some extra weight in case. Here's an illustration of the same formula, but in a graphical format. I'm showing the stress applied and the load. When you apply the load, it produces a stress. And as I apply the load, the maximum load is going to see in service here. That's a stress caused by that load. So say it's going to see 1 million pounds in flight. Well, the stress produced by that is this much. But you know the strength of the material. If you divide the strength of the material by the factor of safety, it drops it to this. And you want to make sure that this is greater than 0. And if it's not, you have a problem. So I'm showing this one here graphically. So you can get a concept of what a margin of safety is doing. So some industry will use a higher factor than 1.5 and just giving you some key numbers. If you test, those are good numbers. If you don't test, some industries will use a factor 2.0. Say it's a pressure vessel that can be safety, a lot of safety concerns. You may have to use a 4.0, 3.0, depending upon the industry that's regulating you, right? But the factor safety can be very high depending upon the application.
Okay.
Great. So looking at how this is done in the aerospace industry, it doesn't mean that civil engineers do it the same way or mechanical engineers, but I'm just giving you a perspective from industry, from my area. But it doesn't mean it applies to all areas, right? So you try to predict the highest possible stress that's going to see in flight, that goes here. The factor safety is trying to account for things that we just don't understand. And also, no analysis is perfect. Plus, there's a lot of variability in the design. That goes in the denominator. And then you have the strength of the material, which is when things break. So that has to be greater or equal to 0. That's key. Okay, the margin should be greater or equal to 0. I advise against making the margin too close to 0. Not a good idea. Here's like a flow chart that kind of brings everything together so you can kind of see it. You basically identify the critical failure modes of the design. You have the CAD model. You have the geometry, radius, everything you need. You have the pressure. The hoop stress for a pressure vessel like this is PR over T. Pressure times radius divided by thickness gives me stress. And that's hoop stress is this stress. I'll cover that later in this course. But just kind of give you a perspective of how this works. Okay, so if I know this pressure vessel, I know there's pressure inside here. P, I can put that into this formula. I know the radius, I know the thickness, I can tell you the stress. I can then go to, say, these handbooks and get the strength. I know the factor of safety says aircraft, so it's 1.5, or let's just change it. Say it's a ground system, mechanical engineering, ground lifting system. So the regulation tells us 3.0. I bring this here, I bring this here, I bring this here, and I calculate the margin. So margin in this case is the stress, the strength, divided by the stress predicted by my model, which is a very simple formula, times the factor of safety minus 1. And we want to be that to greater than 0. That's the preference there, okay? Here's a more complicated problem that I worked on back in the day. Here's a CAD model of a composite sandwich structure under loading conditions. It has temperatures applied, limit loads applied, external loads. I know the stacking sequence of the composite. I take that CAD model, I apply their loads, and I mesh it so that I have those elements that is basically showing the domain here. The properties need to be inserted, like the modulus and all this other stuff. Those is things that you measure, like I said before. The strength of the material is going to become important later. I run my model with those temperatures and external loads. It produces a very high stress here in this region that you can see. In that region there, that's gray. I can validate that against testing here. So I want to make sure my model matches the test. We want to make sure it does a good job of explaining what happened in the test. And if this is good, then I proceed, take the strength, the factor of safety, and calculate my margin. In this case, the formula will be stress, the strength, divided by the stress from my model, the highest stress, times the factor of safety, minus 1. I want this to be greater or equal to 0. That's your margin of safety there. So in real life, for composites particularly, you have to do a lot of testing at the coupon level and build confidence at this level before you go to a more complicated system that if you were to fail, you lose millions of dollars. But if you learn your lesson with more samples at a smaller scale and you validate your models one step at a time, then once you get to this point of a large scale test, you're more successful. But if you skip all this testing and analysis and you jump straight to here, you could have a failure which will set you back quite a bit. So it's a matter of deciding what the right thing to do, what's the balance that you want, and ensuring that you're able to then do a good job of performing a test that validates models that can then be used to ensure success when you get to this point. And we call this the building block approach. And it's a great approach used in industry in general, in the aerospace industry, but also adopted by other industries as well. I hope you enjoyed this talk, and we'll then move to more example problems.